This is a video now on RC circuits. So an RC circuit is one that has a resistor and a capacitor in it. Let's say I have a battery like this, and I hook to that a resistor and a capacitor. We'll give this resistor, we'll go, that could be a kilo ohm, and our capacitor can be 1 millifarad. So what's going to happen is, right at first, we need to bring a switch into this. So there's our switch. Right at first, the switch is open and the capacitor is completely discharged. Now, capacitor, we said, was something that's going to hold charge over time. So what I would like to do is close this switch and see what happens. When I close this switch, I'm going to start to have current flow. So, closing the switch, call this time equals 0. And now, current starts to flow. That current is going through the resistor, that's completely fine, but we've got a gap in the middle of a capacitor. That's what a capacitor needs. So I am pulling positives off of this bottom plate, bringing them around and dumping them onto this top plate. Again, I know I've said it before, I'm not actually pulling the positives around, but when we are defining conventional current as the direction of motion of positive charge, it's easier to just talk about positives moving with a bit of an asterisk on it. So over time, this top plate is going to become positively charged, this bottom plate is going to become negatively charged. The first charge that we dump onto that top plate isn't going to be any kind of difficult to do. The second charge that we dump on there, now there's already an extra charge sitting there, so now there's something fighting us. Now it's not fighting very hard, but it's doing something. The fifth charge, the 12,000th charge, now we're starting to fight an actual buildup, and eventually the forward push of the battery is going to not be enough to push an extra charge onto there. So after a long time, the capacitor is charged up. And now my current has dropped off to 0. I can do the short time, long time thing and say at t equals 0, the capacitor effectively acts as bare wire. After a long time, the capacitor effectively acts like a broken wire. So over here, my total current is going to be E over R, just like Ohm's law. Over here, my total current is going to be 0, just like it would be if I broke my circuit somewhere. That's good for the initial time and the final time, but there's a lot of time that happens between 0 and infinity, and so we need to talk about that. There is something that we are going to define called a time constant. Time constant gets the letter tau because we are far enough removed from torque to where we don't feel bad about reusing that letter. And it's equal to R times C, and it gets units of seconds as it turns out. So a resistance of 1,000 ohms times 1 millifarad equals 1 second. Now I want to see what this time constant actually means, like what it does. Right at first, So let's make a column for time, a column for number of time constants. We will say the charge on the capacitor, Q cap, and we will say the space left on the capacitor. So space left. Might not sound very sciencey to say that way, but that's okay. After 0 seconds, no time constants have gone by. The charge on my capacitor is 0, and the space that's left is 100%. After 1 second, now I said my time constant was going to be 1 second, so these will line up. After 1 second, one time constant has gone by. If this were 2 seconds for a time constant, then I would need a 2 here. The charge on my capacitor, I'm going to have picked up 63% of my charge, which means my remaining space is 37%. After 2 seconds, 2 time constants will have gone by, and I'm going to have used up more of my space. The space that's going to be remaining is going to be 0.37 squared, and then I'm going to turn that into a percentage. So 0.37 squared is 0.1369, so 13.7%, and then what's left here is 86.3%. This thing is quickly filling up. After 3 seconds, 3 time constants have gone by. The amount of space that's remaining is 0.7 cubed, which is 0.0506, so this is 5.1% roughly, which means I've got 94.9% filled. If I go one more, I go 0.37 to the fourth, and that gives me 0.0187, so 1.9%, which means I am 98.1% full after 4 time constants. That's pretty close to full. I can wait until infinity, and at infinity I will get to be almost completely full, but well, at infinity I will be full. I'm just not going to get there, right? But after 4 time constants, I'm most of the way there. After 5 time constants, I'm 99.3% full. This is 0.37 to the fifth is going to give me about 0.7%. That's after 5 time constants. So then I keep adding, and it's not going to make a whole lot of difference anymore, which means my graph, if I were to graph this thing, I would say charge on the capacitor, time, and let's throw those time constants on there, right? 1, 2, 3, 4, 5. The maximum charge I'm going to get on my capacitor, I know, is equal to C times V. I'm talking about the charge, or the voltage of my battery, so I'm going to throw an E on there. So if I've got a 12 volt battery, and I've got that 1 millifarad, I'm going to get 0.012 coulombs, which again is a lot. So over here, I'm going to get 0.012 coulombs. At 5 time constants, I will have pretty much reached this. At 4 time constants, I'm really close. At 3, I'm still really close. 2, I'm starting to drop off a little. 1, I'm down to like 63%. So I'm going to get a curve that looks like this. That's going to asymptotically approach, but never quite reach that 0.012 Coulomb mark. This means it would be helpful to have some kind of a measure here. So for some amount of time, the number of time constants that's gone by is t divided by RC, or if you like, t divided by tau. The space left is 0.37 to the power of t over tau. So when this is 5, this is 5. And then the storage on the capacitor, that's just going to be 1 minus the space left. So 1 minus 0.37 to the t over tau. That's that part. What I can do also is let this thing discharge. When this discharges, what I'm saying is now I'm going to use my capacitor as a battery, effectively. Let's keep this capacitance the same. It's the same capacitor, so 1 millifarad. And let's make this thing now 2 kiloohms. So now my time constant is 2 times 10 to the third ohms multiplied by 1 times 10 to the minus third farads equals 2 seconds. This thing starts off completely full. So if I copy kind of my same table, if I say time, number of time constants, charge on the capacitor, and space left, space remaining, at time t equals 0, no time constants have gone by. The space, or the charge on my capacitor, is 100%, and space remaining is 0. After 2 seconds, 1 time constant has gone by, because each time constant's worth 2 seconds. The space on here is going to be 37% of my charge, so the space remaining, the empty space, is going to be 63%. After 4 seconds, I've had 2 time constants go by, and now I'm going to actually just start copying values. I'm going to have that 0.37 squared is 13.7. Which means over here I've got 86.3% empty space on my capacitor, and so on. Which means if I want to plot this one, because graphs, for a discharging capacitor, it's going to look something like this. And again, after about 5 time constants, we say this thing is about as empty as it's going to get. We're beyond 99% empty. So we call that good enough. Now the charge left on my capacitor, I've got T still here. I've got T over RC, or T over tau. Over here, I'm going to have 0.37 to the power of T over tau. And over here, I'm going to have 1 minus Q cap. That's charging and discharging a capacitor, and that's really pretty close to what I need. I can talk about the current running through this thing too, which is worth having. So the current running through this guy, we're going to have our maximum current. And E is that opposite of a natural log type of number, so this is a constant. Imax, the maximum current that I could possibly have, is E over R. So I get a function that looks like this. This side was for charging a capacitor. Now for discharging a capacitor, I actually get the exact same function. But my maximum current, because I don't have a power supply in there, I just have my capacitor. I know I'm going to have a Q equals C V. So my V is C is Q over C. Q over C acts as my voltage. I need voltage divided by resistance to give me current. So Q over CR, or Q over RC, is what's going to go in there. That's RC circuits. That's all we need.